Hello everyone, today we are going to talk about 1D elements. The first and the simplest type of 1D elements is a bar element. We're going to use the direct approach to solve problems with bar elements. I'm going to explain to you the procedure using this example. So here you can see a bar with changing cross section. We are going to change this into a finite element format of it, a finite number of elements. So we are using 4 elements. So 4 elements we will have 5 nodes. So you can see that the number of nodes is equal to the number of element plus 1. And as we explained in the previous lecture, each element, a bar element, can be simplified to a spring element with a constant and then 2 nodes on each side. We need to identify the spring constant or the equivalent stiffness. So we found that the equivalent stiffness for a bar under axial load, whether it's in tension or compression, is EA over L. E is the elastic modulus or Young's modulus, which is the same throughout our system. So if we use one value, cross section is a tricky one because it changes. So here we have already found the cross section for each element, and the length. So if we are dividing our system into 4 equal elements, so if it is 10 inch, each element would be 2.5 inch. So we can find our element stiffness. We have 4 elements, so we found 4 different stiffnesses here. To form our finite element equation, we need to draw the free body diagram. I'm just going to draw the free body diagram of the first element, but the other elements are going to be the same as well. We're going to assume that U5, the displacement at 5 would be higher than the displacement at 4, and that would be higher than 3 and 2 and 1, and the displacement at 1 would be 0. This assumption means that our elements are going to be in tension. So we have force F1 and F2 acting on our system. The two forces are the same because we have equilibrium. We have K1 U2 minus U1, which is the spring equation, spring constant times the deformation, the difference between the displacement of node 2 minus node 1. I could flip the direction of the force F1 and then write it as U1 minus U2 rather than U2 minus U1. We usually write it this way because then the two forces are in the same direction. So for a node, I can easily write the equation, but if I want to have an equation for the whole element, because element has 2 nodes, I need to write it in a matrix form, because my element has 2 forces, F1 and F2, and it has 2 nodal displacement. So F1 would be equal to K1 U1 minus K1 U2, or K1 U1 minus U2. So that's this equation. And the second row will represent this equation. So here, K, I can factor K1, that would be 1, negative 1, negative 1, 1. You can see that the stiffness matrix would be symmetric for us. And K is the value of EA over L. Not only I have one element, but I have multiple elements. So I found the stiffness matrix, a local stiffness matrix for my element 1. But if I want to combine the stiffness matrices and find the stiffness matrix for the whole system, I need to write my local stiffness matrix in a global form. So in a global form for the whole system, I have 4 elements and 5 nodes, which means that I have 5 nodal displacement. So my stiffness matrix would be 5 by 5. So I need to place this local stiffness matrix into a global form. And to do that, you can see that this stiffness matrix is relating F1 and U1 and F1 and U2 and F2 and U1 and F2 and U2. So it will be placed on the top left part of my global stiffness matrix. And I've written here the nodal displacement and also the nodal forces, so we know the relation between the two and we know where to place it. This is the first element, is dealing with nodal displacement 1 and 2 and forces 1 and 2, so it should be placed here. The second element will get the same form, it's just diff constant value of K2 would be different because A2 is different. Is relating forces in 2 and 3, so that's why I'm placing it here. So the second stiffness matrix, local stiffness matrix, will be placed in the global stiffness matrix, and these notations are going to aid you into correct placement of local stiffness matrix in a global form. Remember, still we call it a global form, it's not a global stiffness matrix. It would be a global stiffness matrix when we add these stiffness matrices together. I could do the same thing for the third element and also the fourth element. So I have 4 elements, so I have 4 stiffness matrices, and I've written them in a global format in their correct positioning. Each of them would be relating the corresponding forces with the corresponding displacement. So now that I have all my stiffness matrices in global form, I could write the global stiffness matrix, which is addition of all stiffness matrices. So I have my first matrix plus the second plus the third plus the fourth, each one representing the corresponding element or the corresponding member. If I add them together, the global stiffness matrix would take such a form. So this is the stiffness matrix that we are going to deal with. And we found this stiffness matrix in a direct form. We just draw the 3-by diagram and found the local stiffness matrices, wrote them in a global form, add them together, and global stiffness matrices. And many approaches that we use in FEA for different elements is to find this global stiffness matrix. After this, whatever we talk would be applicable to all elements and all approaches. So the next step is to apply the load and boundary condition. Let's go back to our problem. We can see at node 1 we have the displacement. The displacement is 0. Whenever we have information about the displacement, it means that we have a reaction force. Here the question is telling us the displacement is 0. That means that we have a reaction force here. Also we have an external load P. So these are the two load and boundary conditions that we have. If we apply it to our system, here F1 equals R and F5 would be P, our external load. And for nodal displacement, we only have U1, so that would be 0. So I have applied my load and displacement conditions here. For the solution process, we are solving equation F equals KU. And of course, if we rearrange it, we're going to find the nodal displacement first. U equals K inverse of our stiffness matrix times F. But to solve this equation, we need to just put all of our unknowns in one side. I don't want to have unknown both on the right side and on the left side. If we look at the equation here, I have unknowns here. Of course, the nodal displacements are unknown, and also I have a reaction force here. That would be my second unknown, which will appear here. To solve that problem and this issue, we are going to remove the rows and columns associated with this reaction force. So whenever we have a boundary condition, we know the value of the displacement is 0, therefore we have a corresponding reaction force. We're going to remove the corresponding rows and columns. If we had multiple boundary conditions, we would have removed multiple rows and multiple columns. That way we only have unknown on one side of the equation. Therefore our matrix is reduced into 4 by 4 rather than 5 by 5. So if I want to find the nodal displacement, instead of a 5 by 1, I have 4 by 1. So as we U2, we just removed the row that included U1. Inverse of my stiffness matrix times my load matrix, which here would be P. And then I remove that reaction force. That one is removed when I removed the first row. So after after finding the nodal displacement, now we have to go back and find the reaction force that we removed. So solving FEA, we are removing reaction forces from external loads. We treat them differently because we know the external load, but we don't know the reaction force. That's why they are separated from each other. And reaction forces are determined after refining the nodal displacement. Now that we have nodal displacement, so here I'm writing in symbolic form, but we found these nodal forces, and we know the stiffness matrices. Therefore, we can find the reaction force. So F equals Ku. I just separate my external loads, then the reaction forces. And then I can rearrange the equation saying that R, my reaction force, would be equals to Ku. I have a stiffness matrix. I found my nodal displacement minus the external load, and I find the reaction force. To do that, you need to remember that we removed one row and one column. To find the reaction force, we have to add the rows and columns that we have removed. Here, we are dealing with the matrix, with the total matrices. So we are going to add the rows and columns that we removed. That's an important note that you need to remember. After finding the reaction forces, then we can find the stresses and the strains. As you remembered, we said that the stresses and the strains are the secondary solution, so they have a larger error. Strain is defined as the displacement over the original length. So if the original length is L1, we can find the displacement of node 2 minus the displacement of node 1. That would be the definition of strain. And the stresses, according to the Hooke's law, would be E times epsilon 1. So we can find the stresses on each member, on each element. You could write additional equations saying that we could compare these stresses with the yield strength of the material to see whether the element fails or not, or if it fails, where it fails. Now first we developed our equations for only 4 elements and 5 nodes. But we could develop the equation for an arbitrary number of elements. Here is a free body diagram based on I and I plus 1. So node I plus 1. That could appear anywhere in our system. But the forces are pretty the same as we described before. Is Ui plus 1, the nodal displacement here, minus the nodal displacement here, times the spring constant. Again, if I want to flip the sign of this force, I have Ui minus Ui plus 1. And my stiffness matrix would be the same. I'm just writing my stiffness matrices and my force and displacement based on I and I plus 1 because I want it to be general. I don't want it to be dependent on a specific number of elements. So I could change my number of elements and have the same set of equations. And K here is EALI. The challenge is to find this cross-sectional area because we changed a continuously changing cross-section to a constant cross-section. So our next challenge is to find this cross-sectional area for an arbitrary number of elements. So here I'm showing you 4, but we can develop it based on any number of elements. So if we change the number of elements, so the element length would be simply the total length divided by the total number of elements. So that would be Li. For the element cross-section, would be the width of the element multiplied by T, which is thickness. Thickness is the dimension into the surface, the dimension that we can see. That this W is changing across our bar. So, but we know that if we know the initial width is W1, the final width is W2, it's the linear function. So we can easily find a function and find W based on the location of our element. So W is simply this, I'm writing an equation of a line. W1 plus W2 minus W1 over L. This is the slope. Y minus Y divided by X. Slope times Yi, and then times T, the thickness. So Yi here is changing from 0 to the length of our element. Or if I want to write it in form of a function, L divided by N, that would be the length of one element, I minus 1. So if you are dealing with node 1, yi would be 0. If you are dealing with node 2, then I1, y2 would be here would be L1. So if you plug it in here, we find the cross section at each node. I find the cross section at node 1, then the cross section at node 2, node 3, and so forth. But in our equation, we need to find a cross section of the element, and that would be simply the average of the two nodes. If I find a cross section at node 1 and node 2, then the average, if I take the average, that would be the cross section that I use for my element 1, and that would be the area that would go into my stiffness equation, and the rest would be the same. So now I have written my stiffness equation based on an arbitrary number of elements. In your homework, you're going to change the number of elements from 2 or 3 to hundreds and thousands, and see how the result is changing. Now that I have written the equation in form of I and j and is independent of number of elements, then we could simply do that. And for Matlab, 10 and 1000 element takes a fraction of a second, so that would be easy to find the corresponding displacement. So we explained it for displacement of a bar element, and our nodal variables were displacement, and we used force balance. But same thing, the direct approach is applicable if we want to use the torque and the angles. In that case, the nodal variables would be the angles. Or we could have thermal problems. Here is conduction, so the nodal variable would be the temperature. And in case of the fluid, the nodal variable would be the pressure, and electrical system. So we could use finite element for solving thermal, electrical, fluid problems. And ANSYS has elements that can handle different nodal variables. Here I'm going to go over a couple of helpful Matlab operations that are helpful in FEA for the rest of this course. So here, if I assume that this is my stiffness matrix and this is B's boundary condition, I usually use 1 and 0 for my boundary condition matrix. 0 when the boundary condition is 0, we don't have any nodal displacement, and 1 when we have no information. It doesn't mean it's 1, but for Matlab, to make Matlab understand, I use 1 and 0. Here, the first one, can you tell me what this function does? It removes the second row. Here you can see a comma, so before comma is a row, and then here is column. Before all column, remove the second row. Here, that number 3 is after the comma, so remove the third column. Here we are removing the second and third column at the same time. That's very helpful, because if you remove the second row and then the second and then the third row, then the new third row is technically the fourth row of your original matrix. So it's very important to remove them at the same time. Here we are finding the index where the rows of matrix B is 0. This is the condition saying that when we have two equal sign, whenever matrix B is 0, here everything is happening after the comma, so we are talking about the columns. So for all rows, when B matrix is 0, assign them to empty. This is just two brackets, so removing all the columns where matrix B is 0. Here is for the rows, so you can see you don't need to use find necessarily, just Matlab understands and returns the indices here. And for solving FEA equation, in FEA we use this all the time, KU equals F. I rearrange it to find nodal displacement. That's the first variable that we are going to find. So we can use inverse of K times F or K backslash F, but the two are different. I recommend using this because that uses a Gaussian approach and you will get an answer. So many of the errors that you will receive will probably be related to the fact that you are using inversion of K times F. That's very sensitive to singularity. If your value is very high value, then the inverse of that would be close to 0, or the opposite. If it's close to 0, then you have inverse of 0, that would be infinity. So this one uses a Gaussian approach that will simplify our equations and will give you an answer. And here you're pre-allocating a matrix. If you know that you're dealing with a matrix of 10 by 10, let's assign a matrix full of zeros, but now we have the dimension. So Matlab doesn't have to expand the stiffness matrix gradually one by one. That saves you a lot of computational cost.